Hello everyone, my name is Florian Schwertfirm, I'm from Turbulenz. We are a small software vendor from Munich. And it's nice to have the opportunity to present here our contribution to this workshop. And this is the result of work we did in the last, let's say, half a year or something. It's mainly from my colleague Innocenti, but he could not come here today, and Johannes, who is also here. And today we want to present results or our analysis and our work diving into non-equilibrium wall functions. Of course, one has to, I just want to skip this, one has to keep in mind that wall modeling is very code dependent and very numerics dependent. So this is in our framework. But basically, I want to start with an introduction of what I want to talk. So basically, this is, everyone knows, this normalized in inner coordinates logarithmic law of the wall, and also DLS data plotted there. And usually one can subdivide this into several regions, and one subdivision is the inner layer, which is like here, going up to maybe y plus 120. So let's say 1/5 of the total thickness of the boundary layer. Then there is an outer layer. In the outer layer, you have the dominant turbulent fluctuations in the boundary layer, and in between, you have the logarithmic region. And this is a boundary layer in equilibrium. And usually, you then, in a wall modeled LES, what we use, you say, okay, you have resolved the outer boundary layer. So the turbulent structures in the outer boundary layer are resolved by LES. They are there by the grid. And you model everything which happens in the inner layer. So from this, you directly have a resolution requirement for your wall model LES, where you say your first grid point should be somewhere in the inner layer, or has to be in the inner layer. And then you take a pair of u and y, and then you feed this into any function you want, usually, for example, the logarithmic law of the wall. And now this is one boundary layer in equilibrium, and today there in the literature you find often like hints to boundary layers which are non in equilibrium, which see pressure, adverse pressure gradients, or favorable pressure gradients. And today we try to test wall models and see their effect on the DrivAer results when we say we use wall models from the literature which take into account the pressure gradient. First of all, I want to show some results from our simulations from the last contribution. And here on the left, you see the instantaneous wall shear stress on the surface of the DrivAer. And you instantly see that in most of the regions, you have turbulent fluctuations close to the wall, so on the wall. But there are also regions where there is no turbulent fluctuations. And this is an indication that there the resolution requirement of the first grid point to be inside the inner layer is not met. In theory, the boundary layer should be turbulent almost everywhere, because like a critical Reynolds number is reached after 12.5 centimeters. So maybe at the side mirrors or at the headlights, there can be still a laminar boundary layer, but the transition is, I guess, not the problem in this case, because it's fast and you have obstacles, you have the edges which trigger transition anyhow. This is probably also the reason why you have this turbulent region in the middle of the car, because you have this head-up view. Also, okay, there are some details about the code we use. I think because it's so numerics dependent, this wall modeling thing, one has to realize that we have an inverse boundary code with an octree grid refinement. We have cubic cells with no aspect ratio, so we have really the same resolution in every direction. And this is also the reason why we have to use wall model LES, because we cannot afford to resolve the boundary layer. Yeah, we don't use an aspect ratio, so we cannot use pancake cells, so we cannot only use refine the grid wall normal direction. So basically now we saw this and said, okay, we first want to improve the resolution requirement so that the first point is in the inner layer of our boundary layer. So what we did is, on the left, you see the old result, the old grid, where we said, okay, we compute the thickness of the boundary layer based on delta 99 everywhere on the surface of the car with the total pressure. And then we normalize this thickness by the grid width. And so we see that in the blue regions, so when the blue regions begin, we have 6 grid points or less inside the boundary layer thickness. And starting with red, we have more than 6, and with yellow, we have 12 grid points inside the turbulent boundary layer. And now when we switch back, we instantly see that this 6 grid points is probably the point where turbulence can live. And at least with more grid points, we are sure that the first point is within the inner layer. So using the left information, we refined the grid. We said, okay, we take the complete front and upper half of the SAE body and go from 3.2 millimeter to 2 millimeter. And we coarsened the grid in the lower back part of the SAE body because there the boundary layer is so thick that probably everywhere the first point is inside. So it has roughly the same computational cost as before, with hopefully more improved results because we could reduce the areas where the resolution requirement is met. It's not perfect yet, and we still probably will need more modeling in the regions where we cannot meet it, but definitely the regions where this resolution requirement is met is better than before. And now with this, of course, we did our computation. We compare the drag and lift. You see it in the lower left, and we see that we have, with the new grid, an improvement of the drag compared to the old one, but the lift is actually getting a little bit worse. So the front lift is always good, stays good. The rear lift is a little bit worse, but the overall drag is a little bit closer to the experiments. When we look at the distribution of CP in the center line, the changes are really small. So they are there, but it's more clearly in the integral value. When you look in the friction coefficient, the changes are a little bit more clear because, of course, with increased resolution, the first grid point is closer to the wall. Your wall shear stress computation is different. And in the right on the left, so in this region, probably we are still not perfectly resolved. So we would claim that we have a real improvement here in this area. So the friction with the finer grid, that the grid friction coefficient prediction is better. So now we go to the non-equilibrium thingy, which is the main topic. And basically, we did a literature research, and we realized that this is not it's not clear. So a lot of things are just not really known. And one can cite Larson that basically the effect is small and no one really can prove something. So we just said, okay, we do a study, and we went through the literature and tried to find all non-equilibrium wall models which are there. And we were quite surprised because, first of all, what you see here, so this is probably the only and main important slide of my whole presentation. What you see on the left, there's an adverse pressure gradient boundary layer. On the right, there's a favorable pressure gradient boundary layer. The dotted lines are taken from DNS. And so the dotted lines are the DNS data of a non-equilibrium boundary layer. And as a reference for an equilibrium boundary layer, you have to look at the blue line. This is the logarithmic law of the wall. So you see that in both cases, in the DNS, we checked, there are a lot of experimental data around which show the same thing. So we just pick the DNS so that the picture is clearer and that you're not overwhelmed by 200 curves. The deviation from the equilibrium state is really, really small. So this is one adverse pressure gradient normalized, but you can also find higher ones, but the deviation gets a little bit further, but the deviation is really small in the experimental results, in all the experimental results we found. This is the first thing to notice. The second thing, we were surprised that there are cited wall models that when we plot them, they have a completely different effect. So basically in these kind of plots, the wall shear stress, when it increases, the curve goes down. When wall shear stress is decreased by the model, the curve goes up. And you see that there are wall models who decrease the wall shear stress, and there are wall models who increase the wall shear stress. So they really contradict each other. In experiments, it's always like this, that in the adverse pressure gradient, the curve goes down, and in the favorable pressure gradient, the curve goes up. You still have to keep in mind that we really talk about here. So what happens here, this is resolved anyhow. This is in the outer layer. So this we need to only look at this region usually. So we were quite surprised, and what we did now is, okay, there are two wall models which we picked because they go into the same direction as the experiments. This was the own motivation. We have picked the Nichols wall models, which is the lila with the turquoise, I don't know. And the red curve is the PGE wall model. And so we picked these both two wall models and, implemented them. These are the formulas. And we can just skip it. We can give them to you, but basically they modify these algebraic equations, the PGE scales, the wall distance in order to increase the wall shear stress. The Nichols changes the constant and a little bit the slope according to this critical Reynolds number. What's interesting to note is that there is a free parameter in the PGE which you can tune. You can increase the effect or decrease the effect. And also that the PGE is already changing something in an equilibrium boundary layer. This is maybe also interesting to keep in mind. We implemented it, we tested it on a 2D turbulent case with an induced pressure gradient, and we compared to the equilibrium wall model, and we see the expected changes. We saw that in the adverse pressure gradient, the wall friction is increased. It's stronger increased with the PGE compared to the Nichols. So we tried to check to make everything correct. And when we apply it to the DrivAer case, we see more or less negligible or no effect on drag and lift. I would say it's within statistical noise. One can take a closer look into the curves, and then, of course, one sees regions where the wall model changes something. Here, you cannot see the difference between Nichols and Locklow. They are really on top of each other, and you can expect it when the experimental difference is so small. There are some areas where you see a change with the PGE. With the PGE, we explicitly took a high F value of 2 times the grid spacing in order to have an effect, to see something. And it's interesting to note that the PGE increases the wall shear stress, especially here when you have strong curvature and when you have a large acceleration. Our main job, what we do is aeroacoustics. Aeroacoustics is mainly depending on turbulent or on pressure fluctuations, and there we have indications that the PGE improves the results, especially when you are coarse resolved. One example is the A-pillar. We have the A-pillar vortex. Around the A-pillar, the resolution requirement is always tough, so we are always under-resolved. PGE increases the wall shear stress here, and this helps us to improve the results a little bit. And we have the indications that also pressure spectra get closer to the experiment when we use the PGE. Basically, that's it. The conclusions, I said everything. I just want to finish maybe with an outlook. The one is the wind tunnel thing. We would be very interested to include the wind tunnel in the simulations, because we see when we include the wind tunnel in our simulations, we see much more variance in drag and lift than with all the stuff we did before. And again, that we do aeroacoustics, and for aeroacoustics, pressure fluctuations are important, and there the PGE is a little bit improving the results. But I won't say that it's really physically induced. It could also be that you have just added shear stress in regions where you need it because you're under-resolved. Okay, that's our results.